All right, so we had the quiz, no calculator over the ideas of chapter 4. Probably half of the points allotted from chapter 4 or from this particular quiz would be about the theorems. Okay, 3 questions where you have to just state the theorems. Okay, pretty much word for word. Make sure you have the correct meaning for that. So we have the extreme value theorem. We had the intermediate value theorem, so those were in section 4.8. And then yesterday we talked about the mean value theorem, which is this right here. Okay? The mean value theorem says if f is continuous on the closed interval AB and differentiable on the open interval AB. So we added in this piece where it needs to be differentiable. No sharp points, no vertical tangents. If you know that to be the case, then the graph is nice and smooth and so forth. If you know that to be the case, then what we said is that there will be a number somewhere in between the endpoints where the slope at that point is equal to the slope between the endpoints. So if I was to draw a line here connecting the endpoints, somewhere in there, there's got to be a point that has that same exact slope. Like so. Or in this example, there would actually probably be a couple of places that would have that same exact slope. Okay, and the importance of this theorem is that it connects f and f prime. We gave an example yesterday where we could kind of use that idea, but that's what the mean value theorem says. Okay, so be able to state those, and then be able to answer some questions about them. So on the first 2 theorems, we had some problems in the homework, so expect some of those on the quiz. Those kinds of things in the quiz tomorrow. True, false, short answer, those kind of things. All right. Now let's go over the homework from the mean value theorem. The mean value theorem. What the first part of the homework, questions 1, 3, and 5 says, if P then Q. You guys who were in computer math, we did a bunch of this kind of stuff. If P then Q, and then the converse, you switch it around. If Q then P, and they wanted you to state if it was true, that the original statement, and some people were confused in the other class on that, the original statement and the converse, you were supposed to talk about each one of those being true. And all this doesn't have anything to do with mean value theorem, but this is just about hypothesis and conclusion, right? And we said if you get an A, then I'll give you a car. Well, if you get an A, you get the car. But if you don't get an A, well, you might get the car, you might not, right? If the hypothesis is not true, then we don't know about the conclusion, all right? So if it's raining, then it's cloudy. Is that true?
Yeah. Well,
I think so, but I mean, I suppose you could argue. There's got to be a cloud somewhere. I mean, so what's cloudy mean? Does a cloudy mean completely cloud covered, or is there any sun peeking through?
okay, so if it's raining, there's a cloud in the sky.
Yes, that's basically how I would interpret that. So I think they intended that to be true. Now, I'm probably not going to ask you one like that. That would be kind of, maybe you could argue that one. I don't want to get into that. But if it's raining, that's cloudy. I'd say, yes, that's true. If it's cloudy, then it's raining. That would not be true, right? That would not be true. So sometimes the converse is not true, even though the original is. Number 3, same thing. If x is greater than 2, then x is greater than 1. That is true. The converse would be if x is greater than 1, then x is greater than 2. And that is not true. Number 5, if f prime is equal to 2x, then f is equal to x squared. Is that true? No. If f prime is equal to 2x, then f does not necessarily equal x squared. Why not? Because of the plus c. It could be x squared plus 5 or x squared plus 7 or something else. So just because f prime is 2x does not mean that f would be x squared. But flip it around. If f is equal to x squared, would f prime be 2x?
Yes.
That would be true. Okay, so again, and sometimes you do get ones that work both ways. Now, I did want to point out 6. I know you didn't have to do that one. But on 6, we talked about this a little bit yesterday. If f prime is less than 0, then f is decreasing. Is that true? F prime is less than 0, meaning negative, then f is decreasing. Yes. What about the converse? If f is decreasing, is f prime negative? Why not? We said that we talked about this yesterday, except we were talking about increasing. If f
is decreasing, is f prime negative? Could be 0, right? Now, not the whole time, because that wouldn't be decreasing, but take x cubed, a negative x cubed, which would come down like this, flatten, and then do this. There's a place there where the derivative is 0. The function's still decreasing. So to be correct, if you flip it, it would have to say if f is decreasing, then f prime is less than or equal to 0. Less than or equal to 0. So that would be a small change, but it would be important. But anyway, that's just some stuff about if and then statements. All right. 8 through 11. Find a differentiable function with these properties or say that none exists. So on number 8, so it says 2 roots and 1 stationary point, but it has to be a differentiable function. So, well, that's easy. That'd just be this, right? Parabola. 2 roots, 1 stationary point. Okay, next one is 3 roots and 1 stationary point. What'd you say on that one? Can't happen. Can't happen. Now, what if it did this? That has 3 roots and 1 stationary point. Not differentiable, right? The derivative doesn't exist because here the derivative is 0, so that's a stationary point. It only has 1, and it has 3 roots. But since it's differentiable, the only way it can have 3 roots is if it turns around twice. And if it's differentiable, the derivative has to exist everywhere, so that means that when it turned around, the derivative has to be 0. So there's got to be 2 stationary points. So it can't happen the way they said it because it's differentiable. If they said is the function, if the function is just continuous, then you could have had that situation. Okay, next one, 2 stationary points, only 1 root. Possible? Take a cubic that does this, maybe. Right? 2 stationary points, 1 root. So that'd be possible. Okay, number 11, infinitely many roots, infinitely many stationary points. Sine or cosine. Okay, then we go to number 19. Now, this is one we did yesterday, similar to this. They give you this f function, x to the 7th. Now it's a big messy one. X to the 7th minus x to the 5th minus x to the 4th. Then what's it say after that? Plus 1. And they say on the interval -1 to 1, explain why there must be a point C in this interval such that the tangent line is equal to a slope of 2. What do you do? Say that again? It's the mean value theorem. Now, when it says explain, you don't have to restate the mean value theorem, but you better talk about the parts of it that are important. In other words, this is a differentiable function. So the hypothesis of the mean value theorem works. And what's the key calculation that I need to do here? Because there is a math thing I need to do here to help explain this. I got to get that 2 involved somehow. I got to do the slope between the endpoints. I've got to calculate the slope between the endpoints because what the mean value theorem says is that there will be some point in between here that has the same slope as the slope between the endpoints. So what that is saying is show that there's a point in there that has a slope of 2. The only thing that would prove, or the only thing that would tell me there has to be a point that has a slope of 2 is if the slope between the endpoints is 2. So I've got to show here that the slope between the endpoints is 2. So I need to do f of 1 minus f of -1 all over 1 minus -1. I need to do that calculation, and I would prefer if you write that out. Make it very obvious that's what you're doing. So when you plug a 1 into here, you get 2. When you plug a -1 into here, you get -2, I believe. So that ends up being 4 over 2, which is 2. Okay, so since the slope between the endpoints is 2, the mean value, and this is a differentiable function, the mean value theorem tells us there has to be some point C in between there that has that same slope of 2. And that would be enough on this one. Now that's a little different than the one we worked yesterday. What did we have to do in the one yesterday? We had to find the C, right? They told us to find the C. So let's say that this question had said, explain why there must be a point C that has a slope of 2. We just did that. Okay, we did mean value theorem tells us, hey, the slope between the endpoints is 2, so there has to be a point in there that has a slope of 2. Then they might have said, now find that point. Then we would do what? Derivative set equal to 2. So we would have 7x to the 6th minus 5x to the 4th minus 4x to the 3rd plus 2. And we would set that equal to 2. Now tomorrow's no calculator, so I wouldn't give you some crazy one like this to try to solve. Oops, what did I do wrong?
Equals 2.
And we talked about that yesterday, right? Because what do we always do with the derivative? Set it equal to 0. Well, this is a case where that's not what we do. Okay, so as I was writing that, I was thinking about that, thinking, yeah, yes, we did. I did it. Okay, because there's got to be some point that has a slope of 2. Okay, so the derivative would have to equal 2. So we would solve this. Now, again, like I said, this is a kind of a crazy one that you would not solve without a calculator. But I would give you one that would be simpler than that, and we could go and solve it and find out and see. Okay, and we did that. We did that in a problem yesterday. All right, so that's basically the mean value theorem. Now you go to number 33. And I couldn't remember if we had talked about, I guess we probably haven't. On 33, basically, do you see how that was a mean value theorem on that one as well? I mean, what was the deal? He went through a toll booth and it took him an hour and 15 minutes to go 100 miles, which means what? His average speed was 80 miles an hour. And so, again, what does the mean value theorem say? The example we gave yesterday is that the average rate of change, that there's some point where the instantaneous rate of change is the same as the average rate of change. So yesterday the example was if I averaged 60 miles an hour between here and Grand Island, at some point I had to be going 60. Might have been going more, might have been going less, but at some point I had to be going 60. So the same thing is true here. If you averaged 80 miles an hour over that 100-mile stretch, then at some point you had to be going 80. So they could give him a ticket. And I've heard stories of that. I don't know if that's really true. I know when we go down to the KU Relays and Track, if you go on the interstate that goes across Kansas, there's parts of it that are tolled, and you have to go and you get a ticket. And you drive through. You guys been through those before? You know, and then you get a ticket and it's punched at where you're at, and it usually stamps the time on it too. And then when you go, when you get off the interstate, then they punch it again. And you know, so if you go 100 miles in an hour and 15 minutes, I mean, you had to have been, speeding. Could they? But I'm trying to imagine. I mean, the funny part of the thing that always cracks me up about this example is that I think about the people who work at those toll booths, and I'm just trying to imagine what I'm saying. Well, you had to give me a ticket because according to the mean value theorem, you were traveling 80 miles an hour. That's what calculus will get you, is a job in the toll booth. All right. Yeah, isn't that good?
It's my dream to work
Yes.
in a toll booth.
Yeah. So anyway, now I did want to look at, if you turn back to 287 there on 15 through 18, take a look at those two problems there. It's the same page. It's the same page as the homework. 15 through 18. I just want to go through those again. There will be some questions like this. There'll be questions where you just have to state the theorem. Okay, so those would be obviously easy to study for us, just to memorize it. Then there'll be some kind of true, false, or it might be true, must be true, can't, that kind of thing, or whatever about using the theorems, the idea of the height, does the conclusion hold? Things like we've had here in the homework. Okay, so just a couple more to look at here on this mean value theorem. They give you the absolute value of x, and they give you the interval from -1 to 2. And so on the first one, on 15, they say, is the hypothesis satisfied with this function from -1 to 2? Yes or no? No, why not? Not differentiable. Okay? Number 16. Is the conclusion satisfied? Now remember, just because it's not differentiable, it's just because you didn't get the A, you might still get the car, right? So is the conclusion satisfied from -1 to 2? this is of the mean value theorem now. Well, how would we show it? What is the conclusion of the mean value theorem? If there's some point that has the same slope as the slope between the endpoints. Okay, so how can I show if the conclusion is satisfied, yes or no? Do what? The slope between the endpoints. Come on, guys, it's the same thing we had to do here, right? Same thing we had to do here. We've got to find the slope between the endpoints, okay? When you look at this picture right here, the whole key is that piece right there, okay? We got to figure out what is the slope between the endpoints and then see if there's some point in between that has that same slope. If it's differentiable function, there has to be. But if it's not differentiable like this one, there might be or there might not. I don't know. So what's the slope between the endpoints? Well, wouldn't the endpoints be here and here? And there's the slope between those endpoints. Is there some point in between there that has that same slope? No. No way. So is the conclusion satisfied? No. Right? I mean, some of you were saying yes, and I don't know what in the world you're looking at. Okay, and some of you are saying no, and I'm not sure you know what you're looking at either. Right? The mean value theorem, the hypothesis is that there is some point in between the endpoints that has the same slope as the slope between the two endpoints. Okay, and there it is, and there is no point in between there. But again, we weren't promised that because it's not differentiable. So it doesn't surprise us that there is one. All right, now 17 says, now let's look at the interval from 1 to 2. So now let's look at this interval. Is the hypothesis satisfied? Between 1 and 2? Yeah, it's continuous, differentiable, absolutely. Derivative exists everywhere. Is the conclusion satisfied? Well, it better be, right? I mean, it better be. If you got the A, you better get the car, right? Or else it's not a true statement, and we know the mean value theorem is a true statement. So it is, okay? Now, and then it says, well, at how many points? Find, let's prove it. Well, what is the slope between the endpoints? 1. So are there any points in between there that have slope of 1? All of them. All of them, right? So that's what it says. How many C's are there? Well, infinite number. Yeah, all of them have a slope of 1. Okay, so, but again, the mean value theorem just says there has to exist 1. So there just has to be at least 1, and there is. There's even more. Okay? But it is differentiable between those two endpoints, so therefore there has to be. Okay? All right. So again, just another example, another way of looking at that. All right. So if we turn to page 288, 289, they've got a little bit of a summary here of what was in chapter 4. So let's walk through this a little bit. Let me just kind of try to go through some things, jot some things down if you want, but about the things I expect you to be able to answer when it comes to the quiz. Now, I've told you that there will be some things that you just, you can't really study for. It's just more about, do you understand the process of things that we've been doing? Okay, I mean, you can't study specifically for certain questions. You can certainly review into yourself what the process was of things that we went through. And then, of course, there's some you can study for very easily by just memorizing those 3 theorems. All right, so on the first one, it talks about slope fields. Now, I'm not going to make you draw a slope field or anything, but slope fields came along with differential equations. Now, chapter 4, now this was before Christmas. Chapter 4 is a culmination of all the kind of stuff we did this semester as far as using derivatives and so forth. All right? And that's part of what, leading into the midterm, part of what this quiz is about, is just making you think about the concepts and ideas of what we've been learning. So, as it comes to differential equations, what are some things that I would want you to know? Well, what is a differential equation? What was the definition? It was a very informal definition. Equation that has a derivative in it, right? An equation that involves a y prime or an f prime or something like that. An equation with derivatives in it. That's a differential equation. What was the solution to a differential equation? The original equation, the original function y. What was an initial value problem? Differential equation with an initial condition thrown in, right? Because that helps you find the c value, the plus c, right? That's an initial value problem. So those were things those are just kind of the main ideas of that. And then we did some T-chart stuff, verifying things were solutions. You're not going to have to go into all that, solving and those things. We've already quizzed on that. But I want you to be able to discuss, to answer short answer or true-false type questions about, those kinds of ideas. Okay, the next thing on top of page 289, limits. We're not going to get into anything with limit problems and so forth. We've solved those, and we're not going to, probably won't ask you about any of those things. Optimization. I've said that I want you to understand the process of optimization, not necessarily to memorize the recipe or the list of steps, but be able to answer questions about the process. For example, where do we look for our max and our min? There's 3 of them. At the endpoints, derivative is 0, which is stationary points. Derivative is undefined. Right now, we'd want to do that in terms of what function. So if the question is where are the max and min of the function f, you talk about where f prime is 0, where f prime is undefined. Where you don't want to say where it's 0, where it's undefined. You know what I mean? Where f prime is 0, where f prime is undefined at the endpoints of the interval, those kind of things. I mean, just stuff like that. Understanding the process. Parametric equations, we won't get into anything there. That was more about solving and so forth. Related rates, again, the process of related rates and those kinds of things. Linear approximation, we didn't even do that chapter, so that paragraph would not be applicable. Newton's method, that's another one, big one. The process, understanding what Newton's method does. Let's just review that real quick. Newton's method is used to do what? It's a method to do what? Find the roots of an equation, the zeros of a function. So if I have a function like so, Newton's method was a way to help me find those values. Okay? How did Newton's method accomplish that? Tangent line. So you would make a guess, and you would, what do we call it, ride the tangent line down to the x-axis. Why was finding where the x-axis, why was finding out where the line crossed the x-axis better than finding where the curve crossed? It's easier to solve, right? We can solve linear equations easier than we can some of these ugly kind of curve equations. So if we could turn it into a tangent line situation using derivatives, then we could find where that crossed. And then if we repeated that, we generally would get a tangent line that was pretty close to where the curve was. And we know that if you zoom in on a curve, it's basically a line. So if we could get the tangent lines close enough through that repeating process, we could find a good approximation of where the curve crossed the x-axis. Now, what were a couple of problems that you had with Newton? Now, you're not going to have to go through a table and do the calculation. You'll have to do that. What were a couple of problems you had with Newton's method? The repeating, the cycling. Like, so if I did this, and then this tangent line went to here, and then that tangent line took me to there, and that took me right back to there, and I just kept going back and forth, right? That wasn't good. That'd be a cycling situation. What else was not good? And if you got up here near the peak and you wrote your tangent line, if it was right on the peak, it'd really be bad. It'd be horizontal, or it could shoot your way out there. Okay, so it might take a lot more repetitions if you didn't get a real good guess if you were near the peak. So those were some issues, some things that could happen. So again, we had some homework questions about that, but be able to just answer questions and discuss that. Yeah. The butterfly effect, the idea, yeah, that's a good one. And that kind of gets into some of those issues with having problems. The butterfly effect was the idea that minor changes in initial conditions can have big changes later on. And so that kind of got into these ones where if I just change the initial guess, I may find a different root, or I may get a problem. So that's what that would be about. Okay, good question. So be able to answer some things with that. And then the last thing there is continuity and differentiability, which is the whole basis behind these 3 theorems that we've been learning. Okay, so we've been talking about what it means to be continuous. Now, earlier we learned what it takes to be a continuous function. 3 things. The function must be defined, the limit must exist, and then the function value must equal the limit. I'm not going to make you memorize those 3 again. I'm not going to ask you that again, but just understand the basic idea of continuity and no breaks and gaps, and differentiability means that the derivative exists everywhere. And it is continuous. Remember, if a function is differentiable, it is continuous. If it's continuous, might not be differentiable. Like the V graph is continuous, but it's not differentiable. So understand the difference there and what those things mean. And then, of course, how those play such a big role in the theorems. And then be able to answer questions about the theorems as well. Not only state them, but answer questions like your homework in these last couple sections. And that's it. I mean, that's enough. But those are the kind of things that I'm going to be asking you about in that. And I don't think it'll take you the whole time by any stretch, because there isn't a lot of solving kinds of things and more writing. And then we'll have packet work time and same thing on Thursday. Now, I was telling the other class, I kind of prepared to tell you about this. Now, a few things may have changed for the better here, but coming into this morning, my wife's mother is in the hospital in Omaha and was not doing well as of last night. Was not doing well at all, and it looked like I may have to. She left this morning and she went to Omaha. It looked like I may have to leave her myself. Now she's better. I mean, she's taken a turn for the better. Now she also took a turn for the better this weekend and then kind of went the other way. So I don't know. It's still kind of. So I just say that looking ahead for the week. If all of a sudden I would have to be gone, I think it's okay. I mean, I don't have anything new to give you, and most of the work is on you at this point, right? So if I happen to be on, the quiz would go on the schedule tomorrow. The midterm would probably go on the schedule on Friday. If I have to have a sub, we would probably on Friday. We would probably for sure do the no calculator one because I'm not sure press the test with the sub would be probably. I don't know how that would go. We have enough trouble around. Okay. But,
It probably would work perfectly.
but anyway, but that would be the plan. But like I said, now as of now, it looks like that's not going to be a problem. Actually, so with that said, why don't we take a look at your packets? Any of the packets. There was a mean value theorem one. Remember we skipped. I think it was in sample 2. Number 11 in sample 2, so you might want to go back and revisit that one. I think it's doable now. I think it's very much like the ones we've been doing where you just need to do the slope between the endpoints and so forth. So don't forget about going back and hitting that one. But we could take a little bit of time here to look at a couple of problems from this latest exam. And then I'm going to give you the last one here today. But again, now remember the first two will be handed in on Friday, and then the last two will be handed in on Monday. That's how we're going to do it. Okay, so this last one I give you today isn't really due until Monday, although it'd probably be good to have get as much practice you can before Friday to get to them. But, so, anybody have some on this one we haven't got to yet? Number 4 in the free response. This one right here? Okay. Okay, looks like a related rate situation. This is at the very end, one of the very last pages of the new packet. Okay, we should certainly have, your homework tonight is basically to be ready for the quiz tomorrow, and work in the packets. Tomorrow after the quiz is packet time. Thursday will be mostly packet time. So really, I mean, with what we should have left in the packets, that's quite a bit. I'm not sure how much you have to work outside class, depending if you're behind much. So, so let's go through this. So it says it's kind of a related rate thing. They give us a couple formulas. Let me write down some things. It says the square is expanding, so the circle is going to expand and maintain these intersection points, which makes sense. There is a center since this is a square. I do know a couple of things here. This would be the diameter. We could call this x. It is a square. So x squared plus x squared would equal the diameter squared. Would that be true? I'm not sure if I need that. I'm just writing down some things. Perimeter is increasing at 8 inches per second, I would call that 8p prime. Perimeter, of course, is going to be 4x here. Okay, I haven't even read the question, which is not that smart, but I kind of know, I kind of have a feeling of what kind of things they're going to ask. Find the rate at which the circumference is increasing, so that's C prime. At the instant when the area of the square is 16, so the area of the square is x squared, so when that is 16, I'm going to be interested in that. Of course, we know x will be 4. So that's nice. Find the rate at which the area enclosed between the square and the circle. Okay, so what would that be? What would be the area between the square and the circle? Be the circle minus the square, right? R squared minus x squared. So that would be an area. Okay, so we got a lot of stuff here. So let's start with circumference. So C prime, well, that would come right from here. So C prime would be what? Pi r prime. Now that's before they even told me about this 16, so that's interesting. So I don't even need that here. I don't even think I'm going to need it. All I need is r prime to find this. Now they told me p prime, and see I got this up here. Now what's another name for d? 2r, so this would be 2x squared would equal 2r quantity squared. What's that, 4r squared? So x squared would equal 2r squared. Would that be true? So if I look at this right here, I got p prime is 8. See, I'm trying to get r involved here somehow. If p prime is 8, p is 4x. What's p prime? 4x prime. Right? Well, if p prime is 8, what's x prime got to be? So x prime's got to be 2. Okay, so now I think I'm getting somewhere, because now I think I can work with this over here. See, I got all these different equations, but I just got to, which is okay, but I just got to know what I need, right? And so I can do the derivative of any of them. I can do the derivative of that, I can do the derivative of that, I can do the derivative of that, right? I can tack on x primes, r primes, whatever I need. So this would be what? 2x x prime. Probably missing something here. It seems like I'm making something right here. Okay. So over here I have 4r r prime. Don't know what x is. Well, yeah, down here, not in part A. But I think what should happen is that it doesn't matter. I'm missing something. Hang on here a second. Perimeter is increasing at 8 inches per second. P is 4x. P prime is 4x prime. So x prime is 2. Oh, that's not right. Find radius where, though? You mean from this? Yeah, but I want to avoid using that because that's in part B, and we're not in that part. So yeah, if I put a 4 here, we could find R. And then, which I think will be okay, but I still think I'm missing something where we don't need, Because if the perimeter's increasing at a constant rate, I think the circumference is too, and I don't think it's gonna matter. Somehow I'm missing something in my picture here with X and R, but maybe I'm not. Maybe I'm searching for something that isn't there. Anybody got a thought? Speak up here. Because I certainly think we can plug this in, and it's not going to matter. But I know there's something here. X squared plus X squared is right. Like if you solve this here. Right there. For the circumference. Okay, so R is 1/2 X squared. And then the square root of that, so R, or the square root of that. Tell me what you got here. Like that?
No, it's 1/2 square root of 2x squared.
Well, okay, R is?
Because the diameter is the hypotenuse of rectangle.
Right. That's where this came from.
So half of the hypotenuse is r, so half of the square root of 2x squared.
I'm not following this. This would be half, this would be R. Is that what you're saying?
No, the whole triangle.
Yeah.
So the diagram again is x squared plus x squared equals the square root of that equals the triangle, right?
Right. The square root of 2x squared equals the diameter.
Yeah, so half of that.
Okay. So half of the square root of 2x squared. Okay, yeah. Okay. Yeah, that's the same thing I have here if you simplify that. But that's fine. So that's R, and put that in here. Okay, I'm with you.
And then you derivative that. And then the x is your cancel away, and then
So let me do a little simplifying on this. So I got pi. This would be the same as square root of 2 and then times x. So now C prime would equal pi square root of 2 is just that. Derivative of that is x prime. And then you're saying put the 2 in for that. P prime is 8, so x prime is 2, which we had here. We'd have pi square root of 2 times 2, okay, or 2 pi square root of 2, which I think is correct.
I'm still lost about R. I didn't see that.
This here, here's what he did is right up here. He said x squared plus x squared, this squared plus this squared, and then the square root of that is the diameter, right? In other words, he just took what I had here and square rooted this. See what I mean? So that's where he got this. And so square root of this equals D. So that's where this came from. So R would then be half of that. And then he put that into there. Okay, now, and that's good. That's what I wanted. I wanted to get something with R and X that wasn't squared. So I actually should have just done that back up here, right? I think what he did is essentially the same thing I had. Let me change to red here. I think when I got to right here, what I should have done is made that be, I should have done the square root of both sides is what I should have done right there. Because here's what was happening. Is I was getting this X and this R in here, we didn't have anything to put in there. Okay? because I hadn't solved one for the other. So right here, I could have done the square root of this. So this would have looked very much the same as what he ended up with. So I'd have had x equals square root of 2r squared, right? Which is the same as square root of 2 times r. You see what I mean? So that's very much what we ended up with over here. Now when I do the derivative of that, I get x prime equals square root of 2 times r prime. And so we knew x prime was 2, so 2 equals square root of 2 times r prime. And so r prime is 2 over square root of 2. Right? See what I did there? So I could have taken what I had right here, this connection between x and r. I could have solved for one of them, then done my x prime. R prime is 2 over radical 2. So now come back to here. So here we had c prime is 2 pi r prime, right? So now I put in my 2 pi, and now for r prime, I put in my 2 over radical 2. And we end up with c prime equaling 4 pi over radical 2. Now if I want to go ahead and rationalize this a little bit, right? Radical 2 times radical 2. So I get 4 pi radical 2 all over 2. And then what happens? Cancel, cancel. I get 2 pi radical 2, which is the same thing we got that. Okay? So what he suggested was again, kind of where I was there. The problem I was getting into is with this x and this r. Now, could you have, here's the deal. When they tell you something like this and don't give you a certain instant when it's increasing or decreasing, what they're saying is it's constant. It's going to be that all the time. Just like here, the perimeter is increasing at 8 inches per second, so that's telling you the circumference is increasing at a constant rate. So it doesn't matter what x and r are. So it would, and that's why I was saying earlier when some of you were suggesting putting a 4 in for x, I think I could have done that. I could have put a 4 in for x here, and I could have solved for the r and put that in there, and I could have put that into what I had originally, and it would have worked out the same as well. Okay, so that's good. We got into a little messier thing than I wish we would have, but that's okay. Sometimes that happens. Sometimes we make it too neat, and it's not always that way. All right, let's look at B. So we had A was the circle minus the square. Now remember what we said, x squared, and I still think I had this, what was it, x squared was 2r squared? That'd be a great substitution to make right now. So pi r squared minus, and now in place of x squared, let's put 2r squared. And now we get it in terms of that one variable. Now, if we wouldn't had to here though, right? Because we could have had r primes and x primes, because haven't we found both of those now? We already found r prime. No, yeah, we did. We had r prime a minute ago. We knew x prime was 2, right? We already found that other stuff, so we could have thrown that in here now. So I wouldn't have had to have made this substitution right here. Okay? But I'm going to. So my derivative would be 2 pi r r prime minus 4r r prime. And now those things that I had brought up a minute ago. Now we knew in this problem, since the area of the square is 16, we know x is 4. If x is 4, what's that make r? Square root of 8. So r is going to be square root of 8. So I can put in here 2 pi square root of 8. What did we say r prime was? Did we have that somewhere? That was 2 over root 2. How does that simplify? Not that we need to, but 2 over root 2, it simplifies pretty nice, I think. Isn't it just root 2? 2 over root 2 is the same as just root 2 if we rationalize it. So I'm going to go ahead and do that. That's root 2. And then 4, and then we said r was radical 8. And then r prime is root 2. Now, you could leave it like this. If this is a no calculator one, now I think on this packet it said you could, this was an old packet back when we could use calculators on everything. So you could get a decimal, whatever. If it was a no calculator, that would actually be acceptable. All right, now it can simplify. Radical 8 is what? Isn't that 2 root 2? Or think of it this way. What's radical 8 times radical 2? Radical 16, which is 4. 4 times 2 is 8. This is 8 pi minus, and then radical 8 times radical 2 is radical 16, which is 4. 4 times 4 is 16. So the whole thing came out 8 pi minus 16. Boy, I hope we're right. That was number 4. Yeah, way to go. We got it. Okay? 2 pi radical 2 for the first one, and 8 pi minus 16 for the second. Sure. I'm just glad I don't have to take it. All right.
We got our
R prime was when we had x squared equals 2r squared, and we did the square root of both sides, which gave us this. So we do the derivative of that, we get x prime equals root 2r prime, and then we knew x prime was 2. That came from this. So when x prime is 2, we put a 2 there, and that gives us r prime. That's how we do it. Okay? Yes, sample 2. Yes, we could go back to there, no problem.
I found the answer for 32 just by guessing the answers they gave.
Sample 2, number 32. This would be on the calculator one. Oh yeah, yeah. This is this one is, I think, a little, and I don't know what do you mean by guess and change? Just with
I
the
just
different
plugged in
answers,
the answers.
which is okay on multiple choice. I mean, sometimes you can get away with that. But this one just kind of, this one's more about understanding what they're saying. So here when it says, they try to help you out, and sometimes when they try to help you out by giving you stuff, it looks like, it almost gets more confusing. But here what they're saying is if you've got X fish, million here, but X fish in this pond or whatever, this lake, and it grows to this amount. In order for there to sustain a steady catch each year, how many are they allowed to be caught? Well, what they're saying is each year they want it to go back to being X fish there. So there's X fish, it grows to this many, and so during the year they want to catch enough to get it back to here. So how many can they catch? Well, it'll be the difference between those two, right? So that's what this line is just this take away X. So what they end up at the year, if they didn't catch any, they'd end up with this many, they started with this many, so the difference is how many they should allow to be caught. Okay? So that's what that subtraction is. It says that's how many are to be caught, leaving X to reproduce each year. What is the number of fish that should be left to reproduce each year, which is what X is, right? X is how many should be left. So what is the number that should be left each year so that the maximum catch can be sustained? So what this is a max problem. Whenever we do a max problem, we have to identify what it is we're trying to maximize. Here we're trying to maximize the catch. So let's call that function C. And that is this function right here. So X times 15 minus X is the function we're trying to maximize. Now if I was doing this, this is a calculator one, so you could actually distribute this through, but actually it's a pretty simple one. This possibly could be on a no calculator part, I think. But if I was doing this, I might just go ahead, especially if it's no calculator, I might do this with it. And so this becomes, 14x minus x squared. So this is nothing more than an upside down parabola. So it's going to have a very simple maximum, probably going to be a one candidate-ish problem. And since it's a multiple choice, you can do it without too much difficulty, even with without a calculator. So the derivative, so where are we looking? To maximize the catch, we're trying to find where the derivative is 0. So we do the derivative, we get that, we set it equal to 0, we get x equals 7. Okay? And since we know it's an upside down parabola, that is going to be the maximum, and so I assume that was the right answer. So it sounds like a lot more difficult problem than it really is. It's just a matter of getting through all the words there. Okay? All right. Anything else? Yes, Rob.
We do 6 on the free response in the newest packet.
In the newest packet, number 6. Yes, we can do part of each of these two parts. Now, this is a really good one for the process of chart kinds of questions. So I want to really talk about that with this one. And it's a good problem for one where you have, these unknowns in here, which is what makes this one tough, because we're dealing with letters, not numbers. Now, but I love this one. This gets to all the important chart stuff we've talked about. Where is F increasing? Well, what do you need to show to show that? And how do we do that? With a number line, right? With the F prime number line. Okay, now go down to B, local max and min. Well, gee, once you have an F prime number line, there's your local max and min right there, right? If it changes positive, negative. Of course, don't forget, on a free response question, we've got to write that out. If F prime changes from positive to negative, F goes from increasing to decreasing, that's a local max. So you'll have to write that out in part B. Part C says, where's a concave up? How do we show where a graph's concave up? Second derivative is positive. How do we show that? Number line, do a y double prime number line. And find where the second derivative is 0. Or, now here's another thing that comes into this problem, is we didn't have this very much on our chart problems, but it also could be where the derivative is undefined. Because I'm looking at this x down here in the bottom, and I'm thinking that that's going to happen. Okay, when the derivative, remember, if you get a sharp point, that's still a local max. And you can have a change of concavity, right, even where the second derivative is undefined. Now, I think you got to be careful of it, and I think that's what we're going to run into in this problem. Is there a change in concavity there when x is 0? Is there an inflection point? There's no point at 0. You can't have an inflection point where there's no point, right? So just because there is a change in concavity doesn't mean that there's a point. So if you look where the second derivative is 0 and there's a change in concavity, say, okay, there's an inflection point at 0, you better make sure that 0 is a point of the original function. And in this case, it wouldn't be. If you had a function like this, the second derivative is going to be undefined. It will show a change in concavity on your number line, but it's not an inflection point because there's not a point there. So those are all things that we didn't really deal with a lot when we were doing the chart problems because all our functions were nice and neat and smooth. But they're things we have to keep in mind. Okay, so this is going to take too long to go through all the different parts, but I want to give you some of the key steps, and then you can go from there on some of those. So first part, we're going to want to do the derivative. Okay, now I'm going to rewrite this as ax plus bx to the negative 1 for my function. So f prime is going to be what? Bx to the negative 2. Now I'm going to rewrite that as a minus b over x squared because that's going to be easier to work with. Okay, so there is my f prime, and I'm going to set that equal to 0 so I can do my number line. Okay, so now I want to solve that. So that's going to be where a equals b over x squared. Everybody with me? This is the part of it that is going to be tough for you. But now that you've seen one like this, hopefully you have a better handle on it. We're going to move the x squared over to here. Again, we get all messed up with these a's and b's. It makes it tough. And x is going to be plus or minus square root of b over a. Now I'm just going to leave it like that. I'm not going to rationalize it or anything. I'm just going to leave it plus or minus square root b over a. Okay? So those are the two places where the derivative is 0. But, and this is the one that we would probably leave out because we haven't done very many of these, and that's why I'm glad you asked about this one. When I go to do my number line, here's negative square root b over a. Here's positive square root b over a. That's where the derivative is 0. But what about where the derivative is undefined? It's undefined when x is 0. We've got to put that in there. Because this may be a situation where we've got a sharp point or something like that going on. Or, how about this? In this particular function, this is increasing, then it's still increasing. Does that make sense? So on an f prime number line, this would show positive and positive. These are all positive slopes. But what if the function was this? Which I think is actually what it is, similar to this. What if the function's this? Slopes are positive and then they switch to negative. Is there a local max there? There's no local max there, even though the f prime number line will show a positive and then a negative. There will not be a local max because there's not a point there, right? Again, inflection points and local max and min are points. There's no point on the f graph, then there's not one. So again, there isn't a point there, but we do need to put it in there. Okay, so now here we go. So now we need something, and we talked about this the other day. So this part we have talked about. What's a number that's littler to the left of this? Put a 2 in front of it. Okay, so as bad as this looks, it isn't going to be all that ugly. I mean, it's going to be kind of ugly, I'll admit. But, okay, and let's go way to the right. What's bigger than this? 2 square root b over a, right? This is one of those problems where you go, oh yeah, okay, now I see why 60-some% is an a. Okay? You know, that's kind of what you think of on one like this. Okay, what's something, let's do the positive, in between 0 and this? There you go, 1/2 square root b over a. And then likewise, negative 1/2 square root b over a. But again, this isn't going to be all bad because think about when we plug it back into f prime. F prime is a minus b over x squared. So when we plug it back in, we're going to get a square it. And that's a good thing because that square root will go away, right? So they're not going to be that bad other than the fact they have square roots and fractions and a's and b's. But other than that, they're great. All right. So what we're going to do is we're going to take this one and we're going to plug it back in over here. Not only that, but when we plug this one, isn't it going to give us the same thing as this one? Because we're going to square it. One's negative, one's positive, so it's going to be the same. So that's going to be nice too. All right, I'm trying to look on the bright side. All right, so we got this. And then down here, we're going to square this. What do you get when you square this? 4 times b over a. Or 4b over a would be a good way to write it. 4b over a. Now, what are we going to do with that? What do we do with this fraction here? Invert and multiply. Now this is another one of these problems that they used to put on because your calculators couldn't handle them anyway, so they let you use calculators, but the calculator couldn't handle it. Ours could with our CADs. This would be a no calculator problem now. Okay? So that's why I'm doing it that way. All right, so we're going to flip it. So this would be a minus, and then this would be b times a over 4b. Oh, that's wonderful. Yeah. I don't even have to pretend now. That's great. Look at that. The b's cancel. So what do you got? You got a minus a fourth a. 3/4 a. Now what did we know about a back here in the beginning? A and b are positive. So 3/4 a is a positive. That's positive. That's positive. Like I said, I don't want to take the time to go through all this, but now the same thing's going to happen here. Except it's going to come out negative. You'll end up with something like negative 3/4 a or something, right? But you'll do the same thing. You'll take this, and then that's going to be the same as that. And so what it's going to be is negative here and here. Okay, so what did you just find? Not only do you know where this is increasing for part A, but you found your local max and min points, didn't you? Okay, now, what about concave up? Okay, so we're going to do the derivative of this. Now this isn't awful. Let me change the blue real quick. So f double prime is, the a would go away. We'd have what? So it'd be positive. This would come down as positive 2b x to the negative 3, which would be 2b over x to the third, and we want to know where that equals 0. When does that equal 0? When 2b equals 0, but what do they say about this? A and B are both positive, so B is not going to be 0. But remember, we also had to talk about where it's undefined. Whenever the bottom equals 0, which is at 0. So our double prime number line is only going to have 0 on it. Okay, actually we can do that real quick. So now, let's put something negative in there and let's put something positive in there. So here's our f double prime right here. So if we put something negative in for x, what do we get? Negative. Put something positive in, positive. Right? So the question in C is, where is the graph concave up?
X is greater than.
Whenever f double prime is positive, which means when x is greater than 0, right? But we had to consider where the derivative or second derivative is undefined, which is, something we didn't always have to early on. Now, are there any inflection points? This is what we talked about right at the beginning. And typically you see a change in concavity, you're like, there's an inflection point at x equals 0. No, on this particular function at x equals 0, there is no point. It's undefined. So there's a change in concavity there, but it is not at a point. It's like an asymptote situation. So, again, knock on wood, see how we did here. I think we did good. I'm proud of us. F double prime is never 0, but although the curve is concave down when x is less than 0, and the curve is concave up when x is greater than 0, there's not a point of inflection at x equals 0 since there is no point on the curve there. Okay? So, anyway, so that's a lot of it right there. You just really just about finishing it up. But those are tough. And so, and often though you get those. I mean, if you've got 6, I'm thinking about the actual AP test now, if you've got 6 free response, a good chance that one of them will get into this kind of stuff. It's pretty common almost every year. Somewhere in there they get into this kind of a situation. Okay? So, you can do that. All right. So, rest of the time, whatever is left, 20-some minutes, go ahead and work on your own, check some answers, ask me more questions if you want. I'll go ahead and give you this packet now. But again, that's, you got plenty to do besides starting that yet, I think, maybe. If not, you're in really good shape. You're sitting around looking for something to do. Wishing you had more to do, right, Brenda? That's kind of what was going through your mind right now.
Yeah, I mean, we're just
Yeah, let's-
so. We want a bit more to do. We don't think
They need another.
No,
Oh my gosh, do you have another one? That would be awesome.
No, I don't like to waste. I don't want to waste paper.
Yeah. Waste of paper? Calculus is never,
Never.
a waste of paper.
Thank you.
Sucker.
Perfect. That is the right answer, man.
If I write that on the right test, will I get bonus?
Well, it's the right answer to a question, maybe
Can I
not
just,
that question.
Squeeze that into one of my essay answers
Just go
tomorrow
for
and see if you actually read them.
Oh, yeah, I read.
Oh, here it is.
Oh, I read.
Trust me, here it is.
Trust me.
Mrs. Larson didn't
But-
read some of that stuff, but here it is. I bet she'll read it if you put it in all caps. That was good.